let's start our today's lecture. The main theme of today's lecture: rank of matrix, solutions of linear system, and the second main theme, vector subspaces. And first of all, I recall some basic definition. First of them, the notion of linear independent system of vectors. We have deal with some vector spaces. For us, the vector spaces is an abstract structure which defined by some collection of axioms. Abstract vector space V, some set with two algebraic operations. First of them is called sum, and we will denote sum by the sign plus, and sum maps the pair of the element of the set, the pair of vectors. The element of the set we call vectors, and the algebraic operation is some correspondence between the pair of elements of this vector space and elements of this vector space. We have some mapping which maps the sets of pairs of vectors in the vector space. Namely, if we have the pair of vector, we can correspond this pair some vectors which uniquely defined and called the sum of these vectors. And the second operation, scalar multiplication. If we have some real number r and some vector, and we have mapping which corresponds lambda real number and some vector v, we maps this pair in the set of the vectors. And we call such vectors scalar product of scalar lambda and vector v. And we have the following axioms. First of 8 axioms. First of this axiom of associativity. If we have 3 vectors, and if we consider the sum first 2 of them and to add the second, this sum is equal to the sum of first and sum second and third vectors. Associativity. The second axiom, axioms of commutativity. U plus V is equal to V plus U. For all U V from vector space V. Third axioms. Exists such element which we call by 0, the element of the vector space such that 0 plus v is equal to v plus 0 and is equal to v for all v from vector space V. Axiom number 4. For all vector V from vector space V exists vector which is called opposite vectors V minus V such that V plus minus V is equal to 0. These axioms, the axiom of the first operation sum. Second two axiom, the axiom of the scalar multiplication. First of them, the product of real number unit and any vector v is equal to v. And the second axiom of scalar multiplication, if we have two numbers the next axiom, if we have to scalar to a real number lambda and mu, and if we times lambda and mu as a real number and multiply this real number on the vector v, and we obtain some vectors, and these vectors is equal vectors which can be obtained multiplying by first real number lambda on the product second number mu and vector v. This product is a vector, and the product of number lambda vector is also vector, and these two vectors must be equal. And we have also two axiom distributivity. If we have two real number lambda and mu and vector v, and if we to add these real numbers and after them this sum multiplying the vector v, this vector is equal sum of the two vectors. First of them the product lambda and v, and second mu and v. For any lambda mu r, any vector v. And last axiom, eighth axiom, the product real number lambda and sum u and v is equal lambda u plus lambda v for all real number lambda and any vectors u v from R. The main basic examples of the vector space, the so-called arithmetical vector space. We denote first example, the vector space of geometrical vectors. symmetrical vectors is a first and most simple example of the vector space. This definition is generalization of this naive example. And the second example, the first algebraic example of such structure is arithmetical vector space Rn. This main for us example of the vector space. What does mean this notation? Rn is as the set of the n tuples of real numbers, n tuples. As a set, and we can define on this set the following two operations. The first of them, sum of what does mean sum? If we have two n tuples of real numbers, the element of this set, the sum is defined as an n tuple of the corresponding sum, a1 plus b1 and so on, an plus bn. Is the definition of the sum of the n tuples. And the second operation, if you have some real number lambda and n tuple as element arithmetical vector space a1 and so on an, the product lambda and this n tuple is by definition is an n tuple any element of this n tuple is a product of the scalar lambda and corresponding element of this n tuple lambda a1 and so on lambda an. Easy to check these axioms. For example, first axiom, if you have three n tuple a1 an c1 cn and the sum first of them by definition is equal and by definition but the sum of the real numbers is associative, and if we to add first two numbers and add second, this sum is equal to the sum of the first number and plus sum of the second and third number. And using the associativity of the addition of the real numbers, we obtain that this sum can be rewritten in the following form. And by definition, the sum is equal and we obtain and we check the first axiom. The same way we can check other axiom. For example, let's check existence 0. Easy to see that n tuple which contain only 0 zero vector of this vector space be such a tuple of real number, every element of this tuple is 0. Easy to see if we add this element to any element of the vector space, we obtain this any element. Is equal if we have some n tuple V opposite element, the n tuple which contain the same element A1, An with opposite sign. With opposite signs. Easy to see also other axiom. It's enough easy task, and we obtain the main example of the vector space, the Rn. The main idea to define such vector space is the following. If we have a geometrical vector space, maybe any vectors in a geometrical space, and if we choose some basis or three non-complanar vectors, let three geometrical vector space, and let E1, E2, E3, E3 be a basis. If we choose some basis, we can decompose any geometrical vector V and present this vector as the linear combination of the basic vectors. And this coefficient of this linear combination is called coordinates. And we can correspond the vectors with its coordinates of this vector. If we have two vectors v and u be other arbitrary vectors of this vector space, we also can correspond this vectors, its decomposition. On basis vectors and corresponds. Also coordinates of the two vectors, of the two vectors. If we add these two vectors, consider the sum u and v. You can decompose each of these vectors, and we can present this sum in the following way. And we can see that this sum of two vectors corresponds the coordinates of the sum is the sum of the corresponding coordinates of these two vectors. And we can see that the operation of addition in the geometrical vector space induces the same operations on the coordinates, and we can natural mapping from the geometrical vector space E3 onto set of the three tuples of the real numbers, and we obtain so-called bijective mappings between these two sets, and this mapping preserves the algebraic operations. More precisely, mapping the operation of sum on the geometrical vector space in the operation of the sum of three tuples, which defined above mentioned way as the sum of the corresponding coordinates of these two three tuples. And easy to see that this abstract arithmetical vector space is a natural generalization of the vector space R3, which corresponds our geometrical vector space. And we obtain the algebraic generalization of the natural vector space, of the natural geometrical vector space. And this enough convenient way for some algebraic reasoning. And in this abstract vector space, we can define the notion of the basis. The basis is the sum set of the vectors which has two properties. First of all, this set is linear independent set of the vectors, and the second, this set is so-called generating system of the vector. What does it mean? Linearly independent and generating. Linear independent is mean that basis some ordering set of the vector E1, En, the element of some abstract vector space. Basis does mean this set linearly independent. This means that if we have some linear combination of this vector and this linear combination is equal to 0 vector, from this fact it follows that all coefficients of this linear combination is equal to 0. Each assertion is equivalent to the fact this 0 vector can be uniquely decomposed as present as a linear combination of this vector, present by unique way. The decomposition of the 0 vector is unique. This fact is equivalent to the following fact. If we can decompose some arbitrary vector x as a linear combination of the basis vectors, such presentation is unique. Easy to see if we obtain two various presentations. We can subtract first of this presentation from second, and we obtain non-trivial presentation of 0 vector. And we obtain contradictory with definition. And if we can decompose arbitrary vector by unique way, and we can unique way present vectors as linear combination of the basis vectors. From this fact follows that zero vector also can be present as a linear combination of the basis vectors by unique way. Linear independence is equivalent to the fact that if some vectors can be present as a linear combination, this vector, this presentation is unique. These two facts are equivalent. Uniqueness of the composition of 0 vectors and uniqueness of the composition of any vectors are equivalent. The first property is linear independence. Second property, the opportunity to the decomposition of the arbitrary vectors, arbitrary vector by basis vector. For if we have any vector x from our vector space V, exists presentation this vector as a linear combination of the basis vectors. And if if the set of the vectors has these two properties, this set of the vectors is called basis in the vector space. Easy to see that the basis is not unique, but the main observation is that the numbers of any basis is the same, and these numbers of the basis, the numbers of the vectors in the basis is called dimension. Now I prove this fact. The theorem, the main theorem, let V be a vector space. Theorem. Let exist basis E1, En in ZV. And let U1, UN be an other basis. Then, I'm sorry, UN. Then M is equal M. Other words, any basis in the vector space contains the same numbers of elements. But exists vector space which contains infinite basis with infinite set of elements. But we suppose in this vector space exist finite basis. The natural generalization of this theorem, if vector space exists two bases, the cardinal number of these two bases is equal. Cardinal numbers. The cardinal number is generalization of the number. Cardinal number can be infinite. We prove this theorem. This theorem is a corollary of the following basis lemma. Let E1, En be a basis in vector space V. If B set of the vectors in V such that m greater than n, then A1, AN linear dependent. Linear system. Linear dependent linear system. Easy to see that our theorem is corollary of this lemma. If we have two bases, let A1, AM be a basis, also a basis, and also M greater than M. We obtain contradictory because this system linear dependent. And from this lemma, we easily obtain that M less or equal M. We can change these two bases and the same way obtain that also N less and equal M. And after that we obtain that N is equal M. And this theorem essentially equivalent to this lemma. And we try to prove this lemma. Proof enough easy. What does mean linear dependence? The element, the vectors A1, AM linear dependent. If exist such numbers lambda 1, lambda n, which not all equal 0, such that linear combination of these vectors with coefficients lambda 1, lambda n is equal to 0. The definition of linear dependence. And our aim to prove that such numbers exist from this set A1, AM if M greater than M. Let's consider the linear combination of this vector. Maybe lambda, maybe arbitrary linear combination. And E1, En basis in our vector space. This means that any vectors E1 can be present as a linear combination of the basis vectors. I have the following decomposition. I have the such decomposition for any vector A1, AA. And I substitute this decomposition in this linear combination. And I obtain the following expression. Using above-mentioned axiom, namely axiom of distributivity, I can rewrite this equality in the following form. Oh, I'm sorry. Excuse me. I have m vectors, and the first index is equal to m. Using commutativity and axiom of distributivity, I can change the order of this element. I can rewrite after them. I can change the order of summarizing. I have such numbers of sum lambda 1 A1 1 E1 plus lambda n A1 n En and so on, lambda m M1 E1 lambda n lambda m M n E. I have such sum. First of all, I summarize the rows in this table. After them, I summarize in any rows, and after them, I can to add this obtaining sum of the rows, and this is my sum. But I can first summarizing in the column on this, and after them to add the sum in the column. And it means that I change the order of the sum, and I obtain the same sum because the operation satisfies the axiom commutativity and associativity. You can change the order. You can permutate this element anyway. and I obtain the following sum. To change the order of sums, I obtain outer sum by j and interior sum by I. And in the interior sum, I obtain I j, oh, I'm sorry, interior sum by m. And after them, I can use the last axiom distributivity, and I can rewrite the last sum in the following form. In the following form. I obtain the sum n vectors, and each of these vectors is the product of some numbers on the basis vectors AG. Vectors Ej form the basis, and this vector is linear independent. But its linear combination is equal 0, vector. It does mean that any coefficient of this linear combination is equal 0. And I obtain the n sum, and in this any sum, this linear combination is equal 0, and I obtain the following linear system, the system of linear equations. And in this linear system, m greater than n. Easy to see that this linear system has non-zero solution because the numbers of unknowns greater than the numbers of the equation. And for example, Gauss elimination methods give us that such system has the non-zero solution. It does mean that exist non-zero tuple of numbers lambda 1, lambda m, which not all are equal 0, such that this combination with such coefficient is equal to 0. That means that this linear system is linear dependent, and this lemma is proved. Okay, and we obtain that numbers of the element of any basis is equal, and this number is called dimension of vector space. It's some invariant of vector space dimension. In the last semester, we proved that the numbers of any basis in the our geometrical vector space is equal to 3. It's a partial case of this abstract theorem. This theorem is natural generalization of this fact. And now we apply this theorem and define the important notion of the rank matrix. Before we consider the example, the main example of the vector space, arithmetical vector space. This theorem is true for any abstract vector space. Partially, this theorem is true for the arithmetical vector space. And easy to see that in arithmetical vector space Rn we have the standard basis, namely E1, E2, this element, easy to see, form the basis in arithmetical vector space. No? Because if you have any element of this vector space, this element can be present as a linear combination. This element, if I multiply this element on A1, this on A2, and this AN, and to add this combination, I obtain this vector. And we have this equality. And this equality means that this element forms the generating system. If I consider the linear combination of this vector, and I suppose that the linear combination is equal to 0, I obtain that the linear combination is equal exactly the n-tuples with element lambda 1, lambda n. And what does mean this element is 0? It does mean it's equal n-tuple of the 0. It does mean that all elements is equal to 0. It means that this linear combination is trivial, has only 0 coefficients, and that means that this element linear independent. And it has a basis. And corollary of this fact, the dimension of this vector space is equal R. I will denote by dim dimension of the vector space. One dimension. We obtain that dimension Rn is equal. And now we apply this simple theory to the matrix and introduce to enough important notion, rank metric, rank of metric. Okay. What does mean rank? First of all, I recall the notion of the linear span. If I have the abstract vector space and let A1, An be some vectors in the V. In the previous lecture, you consider the so-called linear span of this vector. Linear span, by definition, is a set of all linear combinations of these vectors. Maybe. Easy to see that the linear span is a vector space, also vector space, and contains in our abstract vector space. Because if you have two linear combinations, the sum of the two linear combinations is also a linear combination of these vectors and belongs to the set of all linear combinations. If I multiply linear combination on any scalar, on any real number, mu, I obtain also linear combination. It's enough evident, right? Using distributivity laws, I obtain the linear combination also. And we obtain that the set of all linear combinations has two operations, sum and scalar product. And easy to see that this operation satisfied all axioms of our vector space. Enough trivial to check that associativity, commutativity, distributivity axiom are satisfied because this axiom satisfied for all vector space. The question, the axiom are true, the axiom of existence, some element exists zero in this vector space, and we must to check that all vectors exist opposite vectors. The second axiom, this axiom can be enough trivial checked because if I consider the coefficients which all equal zero, I obtain the combination, I obtain the zero combination which is equal zero. It means that zero vector contain in this linear span. And if I have some linear combination and change the sign of coefficients, I obtain the opposite vector. And I obtain that linear span of the vector is the linear span. Is the vector space. Linear span is the vector space. And I can consider the dimension of this vector space. This element can be linearly dependent, and dimension can be less than the numbers of this vector. The system can be generating system, but not linear independent. But I can choose some of this vector which generates this linear span, and this vector are linear independent. This vector forms the basis. Part of this vector can form the basis in the linear span, not all. And correctly defined dimension of this linear span. And we can introduce the two important notions rank of the matrix. Let A be some matrix. This matrix has m rows and n columns. M rows and n columns. And let columns of A okay. And A1 AM be rows of A. Definition. I can consider the linear spans of the sets of columns and rows. And as was mentioned above, the linear span is some vector space. And I can consider the dimensions of this vector space. And the dimension of the vector space of rows is called the rows rank of the matrix, and the dimension of the vector space of columns of matrix A is called column rank of the matrix. Rows rank. Rows rank. Dimension of the linear span of the row. Column rank. The dimension of the linear span of the columns of my matrix A. Dimension of the linear span column row rank is dimension of the linear span of columns rows. The main theorem asserts that these two ranks are coincide. Is the same numbers, and these numbers are denoted by the following symbol and called rank of the matrix A. The main theorem. Definition. This, yes, the question maybe. Any questions? I'm going to prove this theorem. It's not evident. This theorem is not evident. This theorem is based on the basic theorem, which asserts that elementary operation of the matrix is not change the row's rank, the first part. And second part, that is linear, the elementary operation is not change the row's rank. The first part is enough evident. Why? Theorem. First part. The elementary operation of the rows not change the rank, the rows rank. The same assertion for the columns is not evident equivalent. The elementary operation over the columns of the matrix are not change the column row rank. Okay. Matrix. The same assertion for the column, that the column elementary operation are not change the column rank, is enough evident. But non-trivial assertion that the elementary operation are the rows of the matrix are not change column rank. It's not evident. And the same way, the elementary operation are the column of the matrix are not change the row rank. Ideal assertion. The elementary operations are the rows the matrix are not change the column rank. First, I tried to finish this proof, maybe 5 minutes, the main idea. Oh, excuse me. I very shortly to try explain the proof of this theory. The first part enough trivial. What does mean that the elementary operation are not change the row rank of the matrix? I can assert that the elementary operations not change the linear span of the row of the matrix. First of all, let's consider the linear span of the matrix. We have the vector space. If I change any element of this set on any linear combination, I not change the set of all linear combinations. For example, if I add to first row second, multiply on arbitrary number alpha, I obtain the element of this linear span. This linear span of this element. And other element as also belongs to this linear span. From this fact follows such intuition. After that, this element is linear combination, this is this. if I subtract from this element this which multiply on alpha, I obtain this element. Other element is other linear combination of this. And I have opposite inclusion. Such that I prove that two linear spans coincide. If two linear spans coincide, these dimensions are coincided. It's enough trivial. The corollary of this fact: if I apply elimination method Gauss to this for matrix, and after that I obtain some echelon form of this matrix, matrix B. Easy to see that the rows of the echelon form, echelon matrix, are linear independent, and the numbers easy to see if we have some 0 and we have some unit on diagonal. Easy to see that this linear combination of these rows can be equal 0 only if all coefficients are equal 0. It's enough evident. Because thus the rank of the matrix is equal the numbers of the rows of the echelon form of this matrix. We obtain some way to calculate the rank of the matrix, to reduce this matrix to its echelon form and count these rows of the last matrix. And how to prove that column rank of this matrix is equal 0? If I obtain the same echelon form of this matrix, if I prove that column rank of this matrix is not changed, easy to calculate the column rank, and will be also equal these columns, this matrix, form the basis in the set of the columns. So these elements are equal 0. And my claim to prove that elementary operation over the rows is not change column rank. The main idea is enough simple. On the next lecture, I in detail explain and to write this proof. The idea is the following. I'm going. The main idea is following. If we have linear combination of the rows, with some elements x1, xn, and I can consider this n tuples element x1, xn as some vectors, some vector x is coefficients, and I have other vectors with element a1, an. And I can consider this equality as a scalar product, vector x and vector a. Vector a. And this scalar product is equal 0. Okay, let's consider the linear combination of the rows of the matrix A. Column, sorry, column. This combination I can rewrite and I can consider this linear combination as a set scalar product X linear combination of the scalar product matrix A. Easy to see that numbers, the linear independence of the rows of the matrix A, and let I have new matrix B, which obtained from the matrix A by elementary representation. Let B1, the first rows of this matrix, is equal sum first rows of the matrix A and second rows of the matrix A. And other rows matrix B the same as the matrix A. Matrix B obtained by the following elementary transformation. Easy to see that this system equations for matrix A and matrix B are equivalent. If I obtain these two systems are equivalent because the first system I can write in this following form. And easy to see that this equation is equal if this equation are satisfied, this also satisfied because this term is equal to 0. And this term is equal to 0 from second equation. And opposite way, if we have this system, that means this term is equal to 0, and this is a difference between this and this, which multiple alpha. And we obtain that these two systems are equivalent. It does mean if we have linear independence, if columns of the initial matrix are linear dependent, then these columns also linear dependent, and opposite way. The linear dependence of these columns are equivalent. And therefore, the linear dependence of the columns, this matrix, are equivalent. And we obtain that elementary transformation of rows matrix is not change the column rank. And we obtain that the column rank of two equivalent matrix column ranks are equivalent. And as above mentioned, the column rank of the echelon form matrix coincides with its rows rank. And we prove this theorem. Excuse me, I have no time and I finished. Thank you for your attention. Many questions? This theorem I prove very shortly, but I repeat in the next lecture. But if you have the question, I'm glad to answer on this question. If no, let's finish.